Okay, so good morning. Good morning, everybody. That's my attempt at enthusiasm at this early hour of the morning. Okay, so in the last class, which was on Wednesday, apologies, now my program has decided to start its updates, backups, just when I'm going to teach. Just give it a 1 minute. So in the what we have done so far, right? We have talked about positions, velocities, time, length, energy, momentum, force. We've talked about all of these quantities, and we've asked ourselves how do they behave under the space-time transformations, Lorentz transformation, right? And what we find is that there are some quantities which have a non-trivial transformation, right? They are affected by the observer's motion. And in order to properly take into account of the transformation properties, it helps to define these objects called four vectors, right? Because these objects can then be, the transformation property can then be easily encapsulated in such an expression, right? That the four vector in one frame of reference is equal to the four vector in the other frame of reference multiplied by the Lorentz transformation matrix. So using this, for instance, we define the four momentum. The four momentum is mass times rest mass times the rate of change of the four velocity with respect to proper time. Okay. So So we define these quantities, right? X mu is equal to Ct, comma, the position vector. The four velocity is dx mu by d tau, right? Is equal to gamma dx mu by dt, is equal to gamma c, comma, gamma v. Then the four acceleration is dv mu by d tau, right? And this has some complicated kind of expression. And then we can define the force vector, which is mass times this four acceleration, right? And so if we look at the expression for this, right, so if you look at this expression for the momentum, okay, yeah, sorry for that. I should not write it like this. Instead of writing it as mu, I should write it as dp mu by d tau, because that is the correct form of Newton's second law, right? dp mu by, and then p mu is equal to mv mu. I mean, the result is the same as long as your rest mass is not changing. So if your rest mass is not changing, this is equal to m dv mu by d tau. Right? So given that we can define p mu, the forward momentum, in this way, right? The time component is the energy of the particle. P is the free momentum vector. Then the force is the derivative of this quantity with respect to the proper time. And again, using the fact that the proper time is equal to the local time, the time as seen by a particular observer, divided by gamma, the velocity Lorentz factor of that particle with respect to that observer. We can write down the force as this expression, right, where the first term is the rate of change of the total energy or the work that is done on the particle, being done on the particle by the force, times gamma. And the second term is the normal Newtonian force multiplied by gamma, right? Now, since this is a proper forward vector, it will transform under Lorentz transformations in this way. And that means that we can understand how the individual components of the force transform, right? So again, we look at the force and we write down the force forward vector. This is the time component. Then we divide the force into the two components, parallel and perpendicular to the relative direction of motion, right? So this is the parallel component, which we normally call the quote unquote X component, right? And this is the perpendicular component, which would be the quote unquote Y and Z component, assuming the relative motion is along the X axis. Right? So we get these equations which relate the parallel component in one frame to the parallel component in the other frame, and the perpendicular component in one frame to that in the other frame, right? Then we use a little bit of mathematical trickery, which involves these gamma factors. This equation is very important, and you should know how to derive it, right? And where do you get this equation from? You get it by looking at the inner product of two forward velocities. Okay, so I'm not going to go into that. That was done in an earlier class. So if we use this equation and we substitute in these expressions wherever you have this gamma product of gammas, we finally end up with our transformation laws for the parallel and perpendicular components of the force, right? So finally, we have these expressions for the parallel and perpendicular components. Now we can use these expressions to understand how the electric field in one frame of reference transforms as seen by an observer in a moving frame of reference. Okay, right? So these are the transformation equations that we have for the force. Now, so we have some frame of reference O. In this frame of reference, there's a charged particle, right? This charged particle, okay, and also in this expression, let me clarify what these different velocities are. What is v and what is u, right? So v, uh, um, so v is the, let me be a little bit careful about this. Yeah. So this is the picture, right? So I'll copy this picture. So we'll have it for reference. So this is our picture. So you have some frame of reference O. In O, there is some particle Q. Q is moving with respect to O as seen by O with some velocity U. That is what this U is doing over here, okay? What is V? V is the velocity with respect to of the whole frame of reference O with respect to some other frame of reference O prime, okay? Or I probably I always get my relative this it's the velocity of the other frame of reference, the O prime frame of reference with respect to O. Otherwise, you get a different sign in these expressions. Right. So no, actually, I did take into account the sign correctly. So let me adjust the sign of these equations. Minus. That is when O prime is moving with some velocity v, you get a minus sign in this expression. I did the derivation. When I did the derivation in class, I said O is moving with some velocity v, so you get a positive sign. Okay. Now imagine that there is some electric field. Right? There is some electric field, and this electric field will act on the charge, and it will create a force F is equal to EQ, right? This is as seen by the observer O. Now this force, again, we can write in terms of the parallel and perpendicular components. So we'll get that the parallel component of this force, parallel meaning with respect to the direction of motion. So this becomes E parallel and this becomes E perpendicular. That figure is becoming a little bit crowded, but I hope you can make it out for them. So this becomes E parallel times Q. and F parallel becomes F perpendicular becomes E perpendicular. I'm not putting a vector sign on this because there is only one component, and I'm putting a vector sign on the perpendicular because there are two components, right? The Y and Z component. What happens when you look at the system from the perspective of O prime? Well, with respect to O prime, there is the particle's velocity is U prime, where U prime is determined by the velocity addition of U and V, right? U minus V or 1 minus U dot V by C square. So let me just write that down. You'll get U prime is equal to U minus V 1 minus U dot V by C square. Now, this electric field E will be seen as this observer by this observer O prime. So O prime will also obviously say that there is an electric field, but that electric field can have some different components, right? So we'll call it E prime and E parallel prime and E perpendicular prime. So as seen by the observer O prime, there is a force F prime on the charge, which is equal to E prime times Q. And of course, in this, we are assuming that the charge is a Lorentz invariant. Okay, it's like the rest charge or the rest mass. So this means that F parallel prime is equal to E parallel prime times Q, and F perpendicular prime is equal to E perpendicular prime times Q. Right? So now what all we need to do is we need to just substitute these expressions into the force transformation equation. So instead of F parallel, we substitute E parallel times Q. Instead of F parallel prime, we write E parallel prime times Q. Right? Instead of F, we write EQ. So it's easy to see how the electric field, the parallel component of the electric field transforms. So I'll put this here. It's getting a little bit crowded. So I'll just go on the next page, okay? Right. So I just substitute these expressions. F is equal to EQ in here. What do I get? I get Q times E parallel prime is equal to Q times E parallel minus V by C square U dot E times Q over 1 minus U dot V by C, right? So Q will cancel out, Q. So this gives us the transformation law for the parallel component of the electric field. Right. So now in this picture, we are talking about, we have this charge U and it's moving with some velocity u, and here it's moving with some velocity u prime, right? Now we can make a simplification, and the reason we want to make this simplification is the following. When you have a moving charge, right? What will happen is that the charge will also create an electric, it will have a electric field, but it would also have a corresponding magnetic field, right? And how do we know this? We know this because moving charges generate magnetic fields, right? We know this from Ampere's law. We know that if you have a current flowing in a wire, then this induces a magnetic field around the wire, right? Now, a single moving point charge is not the same as a current flowing in a wire. So it will not produce a magnetic field of the same kind, but it will have some magnetic field due to the motion of the charge. So now when we want to explore the transformation of the electric field, but if we have a moving charge, if this charge is moving, if u prime is not zero, then there will be some magnetic field which is generated by the moving charge. So we don't want that. So what we say is that to get rid of this apparent magnetic field as seen by O prime, we require that u prime is equal to 0. Now in this picture, how can we set u prime to 0? So this is u, this is v. In what is the condition for u prime to be 0?
V equal to minus.
V equal to u prime. V equal to u, not mine. Because if we look at this picture again, u prime is equal to 0, right? So that means u is equal to. Right. So u is equal to v. This implies that the charge is at rest with respect to O prime. Okay. So now let's look at this equation again. And in this equation, we will set u is equal to v. Okay, so what do we get if we set u is equal to v? In the denominator, we get 1 minus u square by c square, or v square by c square. Okay, where v is the relative velocity. In the numerator, we get e parallel, minus v by c square times v dot e. Okay. So in this expression, we have V dot E, right? Now, what is V dot E? Let me again draw the diagram. This is the frame of reference. Now I'll draw the O prime. O prime is moving with respect to O with the velocity V. And so that means that U prime is 0. Now there is some electric field here, E. And in this expression, we have E dot U. E dot U is equal to E dot V. So what is E dot V? E dot V is equal to E times V times cosine theta, where theta is the angle between the velocity vector and E. This is equal to E cosine theta times V. E cosine theta is what? It's equal to E parallel. So this is E parallel times V. Right? This is for any two vectors, A dot B can be written as A parallel times B, or it can be written as B parallel times A. Right? So that's all I'm doing. I'm writing E dot V as E parallel, the component of E along V times V. So I can now write E parallel prime as E parallel minus this component. Again, it's a vector, but since we are in the parallel direction, I can write it as a number, V by C square, and this becomes E parallel V over 1 minus V square by C square. Okay. Now in the numerator, what happens? In the numerator, you can take the factor of E parallel common, and you get 1 minus V square by C square. And in the denominator, you get 1 minus V square by C square. So these two cancel out, and you are left with E parallel is equal to E parallel prime. Okay. So this is the transformation. This is what happens to the parallel component. The parallel component of the field does not change. But there is an important assumption we have made here. We have said the magnetic field to be 0 in the original frame of reference, in the O frame of reference. If the magnetic field is not 0, then you will get a contribution. You might get a contribution to this from the magnetic field. Right? We will look at that later. So this is how the parallel component, there is no change. Okay. And now you might ask, well, isn't this a special case? I mean, because I've chosen this velocity to be the same as the velocity of this charged particle. Well, the thing is, we are not interested in what happens to the charged particle. The charged particle is simply a test object. What we are interested in the electric field. Right? So this charged particle is just a tool to allow us to calculate the transformation law of the force. which gives us the transformation law of the electric field, right? This final equation doesn't make any reference to the particle's velocity at all. So you can put any particle here with any velocity. Now, the electric field will still transform in this way. Okay. So I don't want you to think that because of this special condition that u prime is equal to 0, that is why we are getting it. No, this is just a mathematical tool. We use it and then we discard it. It doesn't affect the final result. What about E perpendicular? We can do the same procedure by looking at the perpendicular component of the force. And now again we set the force is equal to EQ. So this tells me that Q times E perpendicular prime is equal to Q times E perpendicular over gamma V over 1 minus U dot V by C square. Now, once again, we have U is equal to V, right? Because we already implied that, we already fixed that to be the case. So U prime is 0, right? So we already have this. This has already been decided to be the condition. So if you substitute this expression in here, what do you get? You get Q. Again, Q will cancel out, right? You get E perpendicular prime is equal to E perpendicular divided by gamma V times 1 minus V square by C square, right? Now, what is 1 minus V square by C square? This is just 1 by gamma V squared, right? So finally, we get that E perpendicular prime is equal to gamma V times E perpendicular. So this is the transformation law for the perpendicular component. So now what you can see is you finally have this E parallel prime is equal to E parallel and E perpendicular prime is equal to gamma V E perpendicular, where gamma is the Lorentz factor of the relative state of motion between the two frames of reference. So what this tells us is that if you look at the electric field, and keep in mind that this is not the same as the electric field of a point charge. This is just an arbitrary electric field. Okay. When we talk about the electric field of a point charge, we'll come to that a little bit later. So I have some electric field here, E. How does this electric field transform as I go into a different frame of reference? Well, it becomes a little bit the angle changes. Why? So this is theta, the angle with respect to the direction of motion. Why? Because the parallel component doesn't change, but the perpendicular component is dilated by a factor of gamma. Okay. So this is the expression for the velocity for the electric field. Okay. Now we can ask uh, what is the magnetic field? What happens to the magnetic field, right? So now I have already said that. So let's look at the magnetic field contribution now. So what we are going to do is, we have already said that B is equal to 0, right? We have said that B is equal to 0 in the original frame of reference. Here B is equal to 0. But here, what will happen? B prime will not be 0, right? B prime is not equal to 0. And that's okay, because remember, the charge is at rest with respect to this observer. So even if B prime is not equal to 0, there is no force on this charge. And so the equations that we have used for the force, they are valid. This equation that F is equal to EQ. Okay. So you might say that, well, I have used F is equal to EQ, but what about the Lorentz term, right? U cross B, and then I would have F prime is equal to E prime Q plus Q times U prime cross B prime. But remember that in the first frame of reference, magnetic field is 0. In the second frame of reference, U prime is 0. So this is equal to EQ, and this is equal to E prime Q. Okay. Right. So now what happens in this case? Let's see. So for this, we will need to use one more expression. So let me give you that identity. This quantity can be written as gamma V squared times 1 plus U prime dot V by C squared. This is equation 4.8 in Steen. And to derive this equation, you can use the velocity transformation expression. And if you use the velocity transformation equation, so I'll leave this to you as an exercise. So basically what you have is, if you look at the velocity transformation, you get, yeah, I'll leave it for you as an exercise, okay? Okay. Of course, you should do that exercise, otherwise you won't understand what's going on. Now, again, when we want to look at the magnetic field, we can once again choose V prime as we wish. Right? Not v prime, but we can choose u prime as we wish. U prime is the velocity of the particle, and as I said, because the particle is simply a probe of the electric and magnetic field. Right? So remember that this u prime, we chose u prime to be equal to v. But u prime doesn't have any effect on the electric field, right? So now what we can do is we choose u prime to be parallel u prime is parallel to v but not equal to v. That means u prime is proportional to v, but the magnitudes are not equal. So what happens in this case? In this case, u prime, the velocity of the particle in the moving frame, will not be zero anymore, right? Because u is not equal to v. But what we can say is the following. So again, if we look at this picture, we say u prime is parallel to v prime. So let me copy this picture and put it on that next page. U prime is not zero. U prime is parallel to v prime. I write the proportionality sign because if two vectors are parallel, then you can write one vector as being proportional to the other vector, right? So if u prime is parallel to v prime, and what we are also going to do is we are going to use this trick, this equation. So we substitute this expression into our force transformation as before. So F prime is equal to Q times E parallel prime minus V E dot U by C square over 1 minus U dot V by C square. And now I use this trick to write U dot V as E parallel minus V E dot U by C square times 1 minus U prime dot V by C square multiplied by gamma V. And similarly, the perpendicular component will become Q times E perpendicular or 1 minus U dot V by C square, which becomes gamma V Q E perpendicular times 1 minus U prime dot V by C square. Now I realize that this derivation is not very transparent. But in the next class, I will discuss a simple thought experiment, which gives you the same result without going through all this mathematics. Okay. Okay. So 1 second. Yeah, and I forgot to put a plus sign here. There's a plus sign here. Plus sign. So what happens now? Well, I've taken U prime to be parallel to V prime, right? So, okay, well, I'll again skip the details and leave those for you to figure those out. Okay, this becomes, and the perpendicular component of the force becomes Q comma V E perpendicular times 1 plus U prime dot V square. So yeah, in this case, we don't need this trick for the parallel component. Again, when U is parallel to V, what will happen is this, in this quantity, the numerator will be equal to the denominator. This factor will cancel out and you will be left with Q with the E parallel prime. Okay. So from this, why are some more reasoning, which is not, again, not so transparent. And in the next class, I'll make it more transparent. We get that the perpendicular component of the magnetic field transforms in this way. So the end result, again, which, as I said, is not a very transparent expression, is the following. E parallel prime is equal to E parallel, and E perpendicular prime is equal to gamma V E perpendicular plus V cross V. All right. So I'll stop here because all this mathematics is, not the same as physical insight. If you want physical insight, then you'll have to wait till the next class. Okay. But of course, you should know how to, what the logical steps I have used in these derivations are. Okay. All right. So I'll stop here for today. And then on Monday, sorry, not Monday, Tuesday, right? We have class on Tuesday, Wednesday, and Friday. So next Tuesday, I will discuss a more straightforward way of deriving the electromagnetic field transformation. You can take a guess without actually going into much of the details. You can make a guess as to what it should be. Well, but again, it requires a little bit of knowledge of, it requires a little bit of hindsight, which, if you start from scratch, you would not have that hindsight. So remember that you have this force law, right? This is called the Lorentz force law. Right. So now, if you just write this expression in a different, with respect to a different observer, moving with some velocity, so instead of V, I should use U, because V I use something else, U prime cross B prime. So this is the force in one frame of reference, this is the force in the other frame of reference, right? Now, if I set u is equal to v, that means u prime is equal to 0. This means that f prime is equal to qe prime, right? And this is the parallel component of the force. And how does the parallel component of the force transform? The parallel component of the force, again, it doesn't change when u is equal to v. So that means that f prime is equal to f parallel prime is equal to f parallel. So you get E prime is equal to E plus Q times U cross P. Okay. No, there's no Q over here, right? Now, and what is U? U is equal to V, right? So this becomes E plus V cross P. So if you just proceed in this very naive manner, you get that the electric field would have this transformation, but we know that this transformation is not relativistically correct, because it tells us that the perpendicular and parallel components, it tells us that, you know, we don't get this expression. We don't get the Lorentz dilation of the perpendicular component of the electric field, right? Whereas we know that the electric field, the perpendicular component is dilated. But this expression does show that we get this V cross B term, right? So what this means is that I have some electric field in this frame of reference, and I have, so what will happen is, because of this relative motion, right, and I have some magnetic field also in this frame of reference. Because of this relative motion, there will be a component of the electric field in the new frame of reference, which will, you will get a contribution from the magnetic field in the original frame. So the magnetic field in the original frame will contribute to the electric field in the moving frame. So in the moving frame of reference, so if, you know, in the original frame, if you set E is equal to 0, and you say B prime is not 0, what happens? You get E prime is equal to V cross B prime, V cross B. You get an induced electric field due to the apparent motion of the frame of reference. So also, so therefore you might suspect that, well, do you have something of this form, V cross E, with, let's say, a minus sign? And the intuition would be correct. And we will talk about this tomorrow. Okay. All right. So I'll stop here.